So we left off with this question of if you had three colors, red, green, and blue, how do you make a regression model that predicts some quantity based on red, green, and blue? And you have a few different choices to make. So one thing you can do is the ordinal encoding. So you could make red 1, green 2, and blue 3. And in a lot of cases, you don't want to do the ordinal encoding. The ordinal encoding only works well if really like blue is 3 times red in some sense. And in most situations, blue will not be 3 times red. And then we also talked about, is it OK to do a drop first? So can you just include a color for blue and red and then know that it's green if it's not blue or red? And that works as long as you use all 3 variables. If you start dropping variables, then that will not work. So that's why it's important to, if you're going to do subset selection, do not drop any columns before you do the subset selection. Your model will drop them automatically when you do subset selection of some kind. So that's important. And there was this issue of what to do with the quality. So the quality is like 1 to 5 stars, or like I think in your actual data set it's 1 to 10, the quality of the house. And I'm going to give you one extra little trick for qualities, for things like that. So here's an extra. If you want, it's a trick. I don't know, this is commonly used for things in order. I'm going to say anytime you have something in order. So in qualities, we don't necessarily want to do ordinal encoding. So first of all, the quality is, let's say for the sake of argument, let's do 1 to 5 stars. We did 1 to 5 stars earlier in the course. So 1 to 5 stars. So imagine you have in your housing data set, there's a rating made by a real life person. Is this a 1-star house, a 2-star house, a 3-star house, a 4-star house, or a 5-star house? How would you encode that in the data? And the first thing is you don't want to do ordinal encoding probably. You can check and see, maybe ordinal would work. But ordinal encoding, i.e. 5 stars goes to the number 5, 3 stars goes to the number 3. Even though it seems kind of intuitive, is probably not what you want. And that's because like maybe the jump from a 4-star to a 5-star is bigger than the jump from a 2-star to a 3-star. And by doing ordinal encoding, again, you're kind of assuming that they go in a linear order, and maybe that's not justified. So ordinal encoding could be possible, but could maybe not be. So you could do one-hot encoding. So this is maybe this. I'll write this assumes linear relationship that maybe doesn't exist. So you got to check and see, is it a linear relationship? If it's not, ordinal encoding is not good. The one-hot encoding, this is, again, very common. So you'd say 5 stars, that would go to the vector 0, 0, 0, 0, 1. So, right, it's not a 1-star, it's not a 2-star, it's not a 3-star, it's not a 4-star. It is a 5-star. And like 3 stars would go to 0, 0, 1, 0, 0. So this would work perfectly well. This is the most general way you can do it. And this would work nicely. There is an issue if you do one-hot encoding and you do subset. So this is issue with subset selection. And it's kind of the same issue we saw before with the red, green, and blue, which is that if you start doing subsets, your subset might delete, like you might choose not to have the 3s, right? So you would delete the 3s. So e.g., if the 3 column is not chosen. Actually, let me make the 5 column not chosen as an example. So if the 5 column is not chosen, so imagine somebody came and deleted this column, right? You're doing subset selection, and that column was not chosen. Well, now you're in a situation where this 5-star looks worse than the 3-star. You see, because the 3-star has a 1 in the 3-star, and this one up here does not have a 1 in the 3-star. So from the point of view of your linear regression, remember your linear regression will do beta hat 3-star times is there a 1 in the 3-star, x 3-star. Is there a 1 in the 3-star? And that's 0 for the 5-star, so you don't get any bonus at all. You get like 0 added on to your total for the 5-star, but you do get some bonus added on for the 3-star. So as soon as you start doing subsets, things kind of don't make sense with the one-hot encoding. And so there's a solution, which is this trick that I call over here, which is, I'm going to call this greater than or equal to encoding. This is related to splines and knots. This is like, so if you want to look it up, this is spline knot features. And what you do is you encode what is greater than. So 5 stars is greater than everything. So that will become 1, 1, 1, 1, 1. 3 stars will become the feature 1, 1, 1, 0, 0. And so the features are x greater than or equal to k stars equals 1 if it's greater than or equal to k stars, and 0 otherwise. Okay? And so what happens is a 1, you'll always have this first one sort of filled up, and then the other ones will go less. I guess you could even get rid of that first one if it's always less, but just for the sake of clarity, let's leave it like that. And the advantage of this has exactly the same information as the one hot encoding. If everything is included, it's exactly the same as the one hot encoding. But if you start deleting things, this one makes more sense. And what will happen is your model will say like, okay, there's not a big difference between a 3-star and a 4-star, so I can just make one category that is 3-star or 4-star, and then I can choose to have it bump up at 5 by just choosing the right columns. So e.g., maybe it chooses only, e.g., might look only at a subset of these. Okay, so we can maybe keep x greater than or equal to 3 and x greater than or equal to 5. And so maybe all of the information in the stars, the only things that matter are if you're 1 to 2, 3 or 4, or 5, those are the 3 categories. And then you have these coefficients, beta hat greater than or equal to 3 and beta hat greater than or equal to 5, that sort of capture this relationship. So this is sometimes called splines. This is a useful way if you have something that's in order to put it in your model without pre-specifying that 5 should be 5 times larger than 1. So it's kind of like a little bit, it's kind of doing the good parts of ordinal encoding without assuming the linear relationship. Okay, so that's a possible trick you can use. And yeah, in general, this is related to something called splines and knots that you might have seen before. Any questions or comments about this encoding? It's just a different way of encoding. And you have to ask the computer for a while. You have to do some commands to make these features come out the way they are. But once you do, it's a useful thing. Okay, I will say you can also do this for other numerical things if you want to try it. Like you can take something like the lot area, right? So if you use the lot area as a number, then that is saying twice as much lot area is better than half as much lot area. But maybe you want to have some cutoff points. So you have like the lot area greater than 100,000, lot area greater than 150,000. You can put those in as features and let the model find little boosts to things. So if you're finding like nonlinear relationships, by adding in these features, your linear regression can capture nonlinear relationships. So that's a useful thing you can try if you want. Okay, questions or comments about this idea, finishing up from last class? All right, one of the other things we talked about last class that we're going to go into a little more detail now is what to do in the following situation, not this one, but this one, okay? Which is what to do when there is missing data. Suppose you're working on a data set and you find a certain data point is missing some of its features, or they are listed as NA or missing or something like that. There are many different ways you can handle this kind of thing. And I want you to just like list as many different ways you can think of as what could you possibly do in a situation like this. Basically, all of the things you can think of will be good in some situations and will be bad in other situations. So you gotta kind of know them all and like know what your options are, so you can think of what would make the most sense in your current situation. Okay, I'll give you 2 minutes to brainstorm what possible things could you do, and put it in the Mathematize as a little list. Oh, maybe I'll say don't put any commas in your list. So just do like spaces. Because if you put like, if one person puts like apple, comma, and the other puts apple, it'll treat it as 2 different words. So no commas, just spaces only. All right, there's only 30 seconds left, but I don't have many answers. Who could use more time? Anyone? Okay, a few people. Let me bump it up to at least a minute over here. So. All right, 30 seconds left. Give me your list of things to do. Okay, let's see. What did people say on what can you do with missing data? And so we're going to brainstorm here with some ideas. Okay, very nice. Look at all these different things. So of course, what you do depends, but it's good to know what the options are, which we're going for here. So some people are saying replace. Some people are saying this word imputation, which is a fancy way of saying replace. So lots of replaces. And there's numbers like mean, median, mode. And these are different things you can replace with. So this is a common thing you can do. This is one of the things you can do, which is to just replace the data with mean. So what to do with missing data. Okay, the options, many options. Options. So imputation means put in a value. So imputation. It didn't have a value. You put one in, and you can replace. So replace with median or mean or something, with mean or median or mode. So you have a house where there's no information about whether or not the house has a pool. What should you put in for that? Well, most houses don't have pools. The mode thing, most houses don't have pools in the data set. So just put in it doesn't have a pool. Maybe that's a reasonable way to deal with your missing data. For other things, you might do the mean or the median. Maybe there's a house that doesn't have a rating. You could replace it with the median rating or the mean rating or something like that. So that's one possible thing. Anyone have any other questions or comments or ideas about this imputation thing? Seems like a lot of people put that in as an answer.
Categorical data.
Yeah.
So do we replace it with a constant to be standardized throughout?
Yeah, so categorical data, the mode would still work. You're right, the mean or the median wouldn't work. I guess the median can work if it's categorical but in order, right? So like quality. But the mode definitely works. For categorical, it turns out there's something else you can do. So this one you can do for anything. And let me see if anybody wrote the special thing you can do with categorical. Okay, let's see. Impute, delete, remove, replace with meaningful values. I want to see if anybody wrote this. Yeah, so somebody wrote replace categorical data with a constant. This is the kind of thing that I want to, is you could make a special category called the data is missing. So new category, new category. So like you could have a category called the data was missing. And then if it's in a category where there's either like, it's red or blue or data is missing, maybe the ones where the data is missing have something different going on than the reds and the blues. So that is a possible thing. It really depends on why is the data missing, right? So is the data missing because it was actually red and we forgot to write it down? Or is it like some color other than red and blue? So that's a valid thing you can do for categorical data as well. And again, sometimes this will apply and be a good idea. Sometimes it will not apply and it will be a bad idea. But it's good to know all the different options. Another one that was very common was delete the row. Delete the row. So if the data is, if you have a lot of data, maybe you only want to keep the high quality data. This really depends on how much data you have, right? If you have tons and tons of data and you're not worried about squeezing out every last little thing, then maybe you just want to delete the ones where some information is missing. Again, you also got to be careful if the ones that are missing are important to what you're trying to figure out and you're deleting them. Maybe there's not a lot of them, but those are the important ones. So deleting it, sometimes a great idea, makes your life nice and easy. Sometimes a terrible idea because you're deleting the actual things that you want to know about. So you have to think about what exactly is happening in your particular situation. Delete the row. Let's see what else people said. Yeah, so sometimes it's better to remove. Okay, some people are saying this nearest neighbors, or when they said replace with mean, median, or mode, instead of replacing it with the mean, the median, or the mode, you can replace it with something that depends on the rest of the data. So in other words, if you have a house where something is missing, one particular value is missing, you could find similar houses, and instead of doing the mean, the median, or the mode from the entire population of houses, you could look at houses that are similar to the one we're talking about. So you could replace with the mean, the median, or the mode, or you could replace with, handcrafted things from similar houses, something from other similar rows. And similar could mean this k nearest neighbor thing, or which we'll talk about later, or it could be some other method. Maybe there's something else that is like really important, and so you want to replace it with something from that. Maybe you do the mean, the median, or the mode, not over the entire population, but over like houses that are in the same price range as that house or something. Again, this is more complicated. So if you're going to do something more complicated, it's more work. You got to make sure you're doing it in a way that is worth the effort, right? So that's one other possibility. Let me see what else people said. Fill in adjacent points. That might be the same kind of thing. Yeah, set to average. Interpolation, this is the same kind of idea. It's like you're missing a value, so you find two values that are nearby and you kind of like average them together or something. Okay, very nice. Ignore, replace. Okay, I think those are the main ones people said. Is there anything else that is, recode is this idea of maybe add a new variable for the one you're missing. I think we got all the ones that people said. Those are the ones that I had. Am I missing any? Does anyone have another idea other than the ones on the board? In weird situations, you can have some weird stuff. I don't know what you would do. Yeah.
If the columns are not important, then we don't need.
Oh, you could drop the whole column. Yeah, this is nice. I wrote drop the row. You could also delete the column. So you can say like, hey.
If the columns are not.
Yes, that's a great. So maybe there's one particular one where like half the houses are missing the data, and you're like, hey, like, what are we going to get from this anyway? If a lot of the rows are missing that one particular column, maybe you want to delete the column instead of deleting the row. That's a very good idea. Okay, and now this is the $1 million. These are all reasonable things to do. Here's the $1 million question. How would you decide which one to do, right? So you can kind of go based on what makes sense. Like in some situations, some of these will make sense and they won't. And so you can come up with a plan. Maybe you can come up with like one or two plans, but how would you make your final decision on which one to do? How to decide? How to decide? What should we do? So let's say we have two plans. We've looked at the list of things. We're like, we could either do this or we could do that. And we're like, how should we pick between this and that? What would you say to someone? Actually, this is so important. Let's make another word cloud. How would you decide? I will add a word cloud because I think this is an important one. So let me close this and add a word cloud. How should we decide what to do? Okay, and this is kind of a general. This question basically applies not just to this problem that we're doing now, but sort of to everything in the course. Of what should we do now? This is the wrong one. Okay, I gotta get present, and then there we go. So it's another word cloud for you. I'll give you 2 minutes. Try to think of how would you make the decision between various options. Yeah, let's do a minute 30. Okay. So think, put your answer in, and then we will discuss. All right, 10 seconds left. Put in your guesses on what you think we should do. How would you decide between different choices? Okay, let's take a look at what people said. All right. Based, something, feature, not seeing one that people are really into. Okay. Pick the one that is the least harmful. Okay, but how do we figure out which one is the least harmful? Based on what is missing and how much is missing. Okay, but like we have two choices. Which one do we go with? Go with the best option. Yeah, which one is the best option? This, you guys are restating the problem. Okay, very good. All right, this one I like a lot. This has a very specific thing. Pick the one with better performance on the test set. And this mentions explicitly the test set. This is one way, anytime you need to make a decision, you can see how would the decision I'm making, how would it affect our error on the test set? And that is one way you can decide what is better or worse. So this, using the test set is a great answer to this question. Let's see what else people said. Based on the situation, test both ways and see which works. So this is a nice way to do it. And test really does mean use it on the test set, right? So try it both ways and then do some kind of experiment where ultimately you measure some test error and see which one is higher. Okay, so that's, I like the test error to see. Yeah, and again, what is a reasonable option will depend on these things. So like, if you're like, oh, I could either delete half my data set or I could just like do this thing, then probably deleting half your data set is not a good idea. And I'm not saying you should test every single thing on the test set, but when you have kind of a choice, you're like, I could do it this way, that would be reasonable. I could do it that way, that would be reasonable. The sort of the kingmaker will be the test error. So let's write that down. So do what is reasonable. Yeah. So think. That is step one. Think. But step two is try an experiment using test error, where you measure error. I mean, to be extra explicit, you measure test error on the test set. Okay. So a good example, maybe you're in a situation where there's only, it's a pretty good feature. You definitely don't want to delete the column. It's a numerical value, so you can't do this categorical thing. And your choices are, I can either delete all the rows that are having this missing thing, or I could replace them with the mean, the median, or the mode. And then you could say, why don't I just run a quick regression? I won't do all the other steps I'm going to do. That would be too much work. But just with the column I'm looking at, if I do it by deleting the rows, that will decrease my data set size. And if I do it by doing the imputation and putting in the mean, that will replace it with something that's not quite right. So both of those are not ideal, but which one is worse? So then you could run a regression, say with all the features, and compare. So e.g., run simple regression, I'll say two ways, and compare. Okay. And then that's not like your final answer to the project or anything, but that will say, okay, well, I did it with deleting the rows, and I got a better answer than by putting in the other stuff. So maybe deleting the rows is the way to go. And of course, like when you have multiple choices to make, you can't test all the possible combinations. But if you're ever unsure, doing a little experiment, doing some kind of test where you measure a test error, that is the ultimate way to make a decision on what is better or worse. Same thing with the hyperparameters we were talking about before, like window sizes. All of that was really saying the test error is the thing we are trying to work on. Okay. I think that was it I had for the discussion on missing data. Any questions or comments or other ideas about this? I think this is like it's hard to talk about this in a sort of math class. There's no theory that will just tell you what to do. It really depends on where the data is coming from and thinking about things in real life. So this step over here, think, cannot be understated. It is really important you do what's reasonable. You should not think of the housing data set as a bunch of numbers. It's really something about houses. You know about houses a little bit, so you have to use what you know about houses to help you figure out what to do. Questions or comments? Yeah.
When we split our data set to test set and training set,
Yeah.
the test set itself can have some misalignment.
That's right. Yeah.
So what should we do with that?
Yeah, That's right. So I think the way I would deal with it in that situation is your test set and your train set, you want the test set to be a representative of the train set, right? Like you want them to kind of come from the same distribution. So if you have issues with missing data in your test set, you should have the same issues of missing data in your training set as well. And whatever method you're using to make a prediction there on the training set, you should do the same thing on the test set. It is true in the project I gave you guys, I have some test ones that I gave you. And for those ones, you have to predict on those things. So you can't choose to drop those. So you'll have to come up with a way to make a prediction for those ones. I don't think any of them are missing data. Now that I'm thinking about it, I'm not 100% sure. But yeah, so your train set and your test set should be the same, so that whatever you do on the train set, you want to do on the test set as well. It is true, you got to be careful with both. Yeah, great question. Anyone else? Okay, here is another common thing. So these are kind of just like common things that come up when you're working on the project. One is normalizing and standardizing. So normalizing and standardizing are operations you run on a feature to just rescale it. So you shift it a little bit and you multiply it by a constant. And normalizing means you make it so the mean is 0 and the variance is 1. So you kind of subtract off the mean. So something that was, in the hundreds of thousands becomes set around 0, and the scale tells you the number of standard deviations. And standardizing means make the minimum value 0 and the maximum value 1. Those are two different ways you can rescale your data. And I wrote a little true-false. When doing linear regression, the results will be better if we first normalize or standardize the data before we run the regression. So give me your true or false on that. All right, just a couple of seconds left. Will normalizing or standardizing help? Okay. Oh no. Okay. What did people say? Drumroll, drumroll, drumroll. Whoa! It is almost perfectly split. True and false, 9 to 10. That is as close to 50% in each category as you can get. Let's do a revote. This time, try to convince your neighbors that your answer is the right answer and that their answer is wrong. I guess if you agree, then find a different neighbor to gang up on. Okay, I'll revote it, and we will vote again. If it helps, think of the equation for the linear regression and how the equation would change if you standardize or normalize. Okay, let me open it up for one more minute. All right, 10 seconds left. Put in your updated guesses. Even if you didn't change your answer, you have to put it in again. And let's see where the vote ended this time. Okay. Oh no. Okay. Da-da-da-da. Ah, even more tied. Okay, let's look at the equation, and that will help us figure out what's going on here. So we're going to figure out the answer, and the secret to this question lies in the equation for linear regression. So let's say let's just do one-dimensional data. So x, we'll just make this a one-dimensional thing. So x is a number, and we're trying to predict y, and we have this prediction y hat equals beta hat 0 plus beta hat 1 of x. And actually, beta hat 0 and beta hat 1 are determined to minimize the sum of squares. So beta hat 0, beta hat is the minimum. Some people call this the arg minimum of the square loss. I'll call this the loss function. I'll say the mean squared error. Okay. So in other words, for every possible value of beta hat 0 and beta hat 1, you get some amount of error, and we choose the ones that minimize the sum of the squares, that minimize the mean squared error. Okay, so that was before we standardize it. Now let's see what would happen if we subtract off a constant. So we take the x values, and we subtract something. So we do y hat equals beta hat 0 plus beta hat 1, and then now we're subtracting from the x's. So let's do x, and we'll subtract off in green some amount, c. So subtracting something off could be the mean. That would be normalizing to make it mean 0. It could be just some like random amount to make it so the minimum value is 0. That would be like subtracting the minimum value. Whatever. We're changing the data set. So before it was x, now it's x minus c. We've subtracted c from every single element. And so that's our new model. Y is beta hat 0 plus beta hat 1. And again, we will compute. Let's call this, let's add some little primes here so we don't mix it up with the first one. And now beta hat 1 and beta hat 0, they are, again, the arg minimum of the mean squared error. The mean squared error. Okay. Right, so it's we find the values that make the error between the y hats and the y's as small as possible. So maybe I should write out the mean squared error. The mean squared error is the difference y minus y hat squared averaged over the sample size. I'll just write with a colon, and then I won't specify. So is the setup clear? This is what we've been doing. And now that you're looking at the equation, does anyone want to tell me what is going on with respect to this question? So what happens when you add a constant, looking at the equation, mathematically, what will happen? Anyone see what's going to happen? And in particular, you can ask, what is the relationship between, what is the relationship between beta hat 0 and beta hat 0 prime and beta hat 1 and beta hat 1 prime? In other words, we did it without adding a constant, and we did it with subtracting a constant. How did the coefficients change? Any ideas? Yeah.
I think some portion of the original beta 0
Yeah.
could go to the beta 1 high.
Yeah, that's right. So you're saying some portion of the original beta hat 0 could go into the beta hat 1. How would you kind of like mathematically see that? Or what would you do mathematically? You're exactly right. There's some kind of relationship between these two things. Yeah, and you have your hand halfway up? Yeah, what's your halfway up?
Y hat is the same.
So y hat is our prediction, right? That's right. So we have x's and y's. So we're given a collection of x's and y's. We come up with a y hat for every single x value by using this formula. And then we find the coefficients that make the difference as small as possible, right? That's the game. You're given the x's and y's, so the x's are the same, the y's are the same. for every possible setting of the coefficients, you calculate the y hat, and then you pick the one that makes the error as small as possible. Yeah. So what can we do? So you said there's some kind of relationship between this one and this one. Something about the beta hat 1 and the beta hat 0. How would you see that? Why don't we try to make this equation look a little bit more like that equation? In this equation, the x is sort of on its own. In this equation, the x is in a bracket with the minus c. So what could we do? What if we expand it out? What if we write it like this? Beta hat 0 prime, the new model, prime just means new, plus beta hat 1 prime. Okay, and then we do times x1, and then minus this c times beta hat 1 prime. Okay, and that equation looks very similar to that equation. What's the difference? Beta hat 1 got replaced with beta hat 1 prime. So actually, the slope of the x's is exactly the same in both models, right? If you are running this model or running that model, the beta hat 1 and the beta hat 1 prime, they mean exactly the same thing. They're the thing you multiply x by. So actually, the beta hat, with or without the prime, the 1 is exactly the same. So this one, with or without, will be equal. They're exactly the same thing. Okay, what about the intercept, the beta hat 0? Well, that's not the same. They're different. They're different. So if you put in a beta hat 0 over here, and you put in the beta hat 0 over here, you put in 7 for both, you're going to get 2 different answers, right? But what you can do is notice that this term plus this term together, that can combine to give that term. So you can write it like this, that beta hat 0 prime plus, or minus in this case, minus c times beta hat 1 prime equals beta hat 0. So this is the relationship. So actually, these are 2 different ways of having the same collection of possible models, right? So you get to choose the slope and the intercept over here, and here you get to choose the slope and some kind of weird combination of the intercept. But whatever solution you find over here, you can find the same and an equivalent solution over here with slightly different numbers. So the numbers themselves change. What you get for beta hat 0 prime will be different than what you get for beta hat 0. But the final prediction, the y hats, will be identical. It will be exactly the same thing. So what is the conclusion? The conclusion is shifting the data does not change the set of models, does not change the possible models. And in particular, it doesn't change the best possible model. Right? So either way you do it, when you add a minus c, you have not changed anything about this stuff. Okay, does that make sense to people? When you do a minus c, you're kind of reparametrizing what you called beta hat 0 now changes to what you call beta hat 0. But it doesn't change when you go to find the minimum, you're going to find the exact same predictions as you found before. Okay. All right, that's shifting. In the question I asked you, it wasn't just shifting, right? It was shifting and what else were we doing? So we were standardizing and normalizing. We were shifting and rescaling. So we were moving the data over by subtracting a constant, and then we were dividing it by something. Maybe dividing it by 100 to shrink it by a factor of 100. And so the question for true or false, shifting does not do anything. The question is, does rescaling, multiplying by a constant, does that do anything? Okay? And you've seen the argument for shifting now. What about rescaling? And let's have you vote for a third time. So, okay? So I'm gonna, if you gotta repeat what I said and see, does the argument still work for shifting or not? Or rescaling. It does work for shifting. Shifting does not change anything, but does rescaling, question mark. Okay, and I will let you think about it and try it. Rescaling? Does that do anything? Okay, let's vote once again and see if we can break the tie. duplicate. Okay, I will give you Okay, so it is open again. Put in your updated guesses. And if you want, you can think about the argument on the blackboard and see what would happen if we rescale it. Okay, most people have answered. Let's see. Only a few seconds left for the last people. 20. Okay, there's only 20 people here. Okay, great. Let's stop this. Okay, and we have 21, so the tie will be broken. Let's see which way it works. All right, now we're in 17 people are in false, 4 people are in true, and the correct answer is false. So very well done. The correct statement when doing linear regression, if you first normalize or standardize, the results will be exactly the same. They will be exactly the same. Nothing will change if you do standardizing or normalizing with linear regression. Rescaling also leaves the data unchanged. So the results will not be better. They will be identical. Also does not change anything. Does not change anything. Okay? And the reason, you can just see it mathematically. Imagine you divide by some other number here. Let's divide by a. Well, then this will get it divided by a. This will get it divided by a. And then I'll just divide by a over here. This divides by a. This divides by a. And so in other words, you have introduced another kind of thing that you have to do. There's another kind of shifting and scaling of the coefficients, but the two things will be identical. So the old thing that you called the slope and the intercept, they will be slightly relabeled. There will be some other linear combination of the slope and the intersection, but it's the same set of models. It's exactly the same models with a different parameterization, and you will get the exact same predictions as the quote best predictions, and you'll get the exact same mean squared error, and so on. So the model will be exactly the same, just kind of relabeled slightly. And in fact, any kind of linear operation on the input data will just become a linear operation on the beta hats, and the final outputs will be identical. Okay, so that's the thing that happens. Yeah.
If you're going to divide by if you're scaling the whole model, why isn't beta 0 affected?
So I took the x and I replaced x with x minus c divided by a, right? And the beta hat 0 prime is what you add on to the whole thing.
So is the slope?
I'll tell you maybe what you're thinking
Is the
of.
slope not going to be beta 1?
Yeah, the slope in the new coordinate system is beta hat 1 prime.
Yes.
Yeah.
But if you do c over a of
Yeah.
1 prime,
Yeah.
that's not the same as without rescaling.
Well, so maybe these divided by a's are not visible. Like this equation equals this equation. I took the divided by a and I put it on the beta hat 1.
Yes, I understand that.
So this is the same.
Yes.
And then what I did is I matched this one to this one by matching what has changed. So the beta hat 0 prime minus c over a beta hat 1, that's this thing, is the same thing as what we called beta hat 0 before. And the beta hat 1 divided by a is equal to the beta hat 1. So just the coefficient in front of the x. Those two are the same. The thing you might be thinking of, another operation you can do, is you could possibly do the same thing with the y's. So if you took the y values And in my mean squared error, I took y and I divided y by, I guess I can't use the letter A or C. I can use the letter B, because I haven't used B yet. If you took the y values and you rescaled them, then you would have to rescale, again, the y hats. So there, if you rescaled the output, then you would have something happening with the thing. You would again get the same model. It would be the same thing. Things would be reshuffled by some different amount. But that might be what you were thinking. If you divide this by b, then you would have to divide sort of everything by b to make it match. That might be what you're thinking of. Yeah, let me delete that. I think that's more confusing than it is helpful. It will work out to be the same thing. And let me erase this funny thing. Okay. Does that answer your question? Are you, or is it still unclear? Oh, it's good. Okay. Okay. Why on earth do people talk about these normalizing and standardizing things if it doesn't do anything? Okay. Well, it doesn't do anything for linear regression. We're going to see in different, more complicated models, it's really important. So caveats. For other more complicated versions, for other things, let's say other methods, so not pure linear regression, other methods, it is important. Okay, so that's like the main thing. Like it really can matter quite a lot in other methods. Another thing is it helps with interpretation. So can help with interpretation. So when you are looking at your data and you're trying to figure out what is going on, what is this thing that I got? Here is one common situation people have. They will say, okay, I ran my regression and I got beta hat, 7 is 0.1 and beta hat 9 is 45. Okay, so they ran the regression on the housing data set and they have a 0.1 and a 45. And then they say, 45 is a bigger number than 0.1, and therefore the ninth entry, the ninth column, must be more important than the seventh column. So therefore, the ninth column is more important than seventh column. Okay, so this is all an example of somebody thinking about their data. So example. Okay. This conclusion is incorrect. This thing that written in red is not correct, it is not true, and can lead you down the wrong path. If you think that 45 is bigger than 0.1, and therefore beta hat 9 is more important than beta hat 7, that is incorrect. What is the problem with what I just said? This is a bigger number than that, but nevertheless, it can be that this one is less important than this one. How could that be? Right? The order of the numbers and the order of the importance are not the same, and there's something missing from the board. Yeah?
The size of the x.
That's right. The thing that is not here is the size of the x. So remember, the coefficients, you should think of them as they're in units of slope of the x's, right? So it's exactly missing the slope of the x's. So this is wrong. Let's cross this out. The thing you would need to do to check is which is bigger. To actually see which is more important, you have to compare beta hat 7 times x7 versus beta hat 9 times x9. So the real comparison that you need to make is which of these is bigger, right? So the total prediction is the sum of all of these things, and so it could be that this term is bigger, it could be that that term is bigger. Comparing the beta hats on their own without the x's is kind of meaningless, right? And then now you have questions of like, well, how big is x7 typically? How big is x9 typically? Right? If x7 is the lot area is in like thousands, but x9 is a categorical variable, either 0 or 1, then it could be that 0.1 times 1,000 is a lot bigger than 45 times 1. Okay? So relative size of the x's matters. Relative size of x's matters. A lot. Okay. And this is one reason that people would choose to standardize or normalize their data, right? By standardizing or normalizing your data, you make it so all of the different x's are approximately the same size. They're all about, -1 to 1, -2 to 2. They're all about the same size. And if they're all about the same size, then you really can directly compare the beta hats. So basically, to get around this issue, one way to get around it is to do standardizing or normalizing, and then you can directly compare. This is like the main reason to standardize or normalize. Okay, was that discussion clear? Any questions or comments about this idea? I think this is a common mistake people make. They'll be like running their regression. They'll be like, oh, this number is only 0.1. Let me just delete that column. 0.1 is so small. How could that possibly matter? But if it's 0.1 times x7, which is typically in the thousands, then that will matter quite a lot. Okay. So it can help with interpretation, and in other models, it's very important. I will also tell you this is a common bug. A common bug. So standardizing and normalizing creates a common bug. Here is the common bug. What people do is they take their training set, the train set, and they normalize it. Let's say normalize it. Okay, so they normalize the training set. So remember, your project, you have two files. There's a training file and a test file. They take their training set, they run, they like scikit-learn.normalize, and they normalize the training set. And when you normalize the training set, whatever it was before becomes x minus, and it becomes the mean of x. Let's call that mu, and then we will divide it by the standard deviation, sigma. So what it was called x before, now it's x minus mu divided by sigma. Then they run all their analysis, they do all their checking, they delete the columns that need to be deleted, they fix all the data, and they come out with a final prediction, and they come out with a prediction, and so they get a model. Get model y hat. Okay, so they have this function, and then they go, okay, the next thing you got to do in this project is you take the test set, let's call the test set x, and then you normalize the test set, normalize the test set. So that becomes x minus mu divided by sigma. And then you apply predictions. So then they take these predictions and they apply them. Apply predictions. Okay. So they do all this, all seems very reasonable. And then the only problem is the predictions are all wrong. Bad. Doesn't work. Really bad predictions. Really bad. Okay, and that's because they have this common bug. This bug also happens with other things, not just with standardizing and normalizing, but I think this is where I've most commonly seen it, is with standardizing and normalizing. Does anyone know what the bug is? I made a big mistake in the sort of setup I described. Does anyone know what it is? Yeah. Go for it.
We need the history of train set to put on the test set. I mean, the z-score of the test set is different with we need to say the z-score when we want to calculate z-score on the test set.
Yeah.
Consider the position on the train.
Yes, that's exactly right. You figured it out. So the problem is the z-score, this x minus mu over sigma, if you calculate it just with respect to the test set, and then the z-score over here, x minus mu over sigma, you calculate it just with respect to the training set, they mean two different things. So in other words, suppose you have a house that is perfectly average, right? A perfectly average house has a score of 0, right? X minus mu over sigma is over here is a 0. So maybe let's say perfectly average on the training set was 1,000 square feet area. So a house that has 1,000 square feet comes out with 0. And then over here, what does a 0 mean? A house that is a 0 over here means also perfectly average, but it means perfectly average on the test set. So maybe on the test set, a 1,200 square foot house was a 0. And now you have a mismatch. You have two things that both have the number 0. You're applying the same model to both of them, but they mean two different things. One of them means a 1,000 square foot house. One of them means a 1,200 square foot house. And your predictions will come out all wrong. And so the thing that really went wrong is that it went without sort of saying this is the mean on the training set, and this is the standard deviation on the training set, and this is on the test set, and this is on the test set. And they're not the same. So you've applied two different operations. You subtracted a number and divided by a number, and here you subtracted by a number and divided by a different number. They're just going to be two different things. So this is the bug. To do it properly, what you need to do to fix it, don't normalize like this. You have to don't do this. You have to take the normalizing, the x minus mu train, and apply it to this guy. And if you do it in like scikit-learn, there's like a thing called a normalizer and you can apply the same normalizer to both. But the easiest way to avoid this bug also comes out with other things. Another example of this is when you're making categorical variables. So suppose you have red, green, and blue, and you say, okay, red is the first thing we saw in the training set, so red is 1, or red is the first column, blue is the second column, green is the third column, and then you do it on your test set, maybe they're in a different order, and then things are all out of order. So that's another way you can have the bug. Here is an easy way to fix the bug. Here's a easy fix, and this is like a kind of a practical thing, which is your first step is to glue the two training sets together. Make a giant data set, which is train plus test glued together. So in other words, you take your training set, you take your test set, and you stick them together and make one big data frame that has all the data all at once. And of course, for the test set, you will be missing the house prices. So the bottom half will be missing house prices. So your data frame will look something like this. It'll have the first little bit will have all the information, and then the last little bit will have all the information but no house prices. So this is your data frame is like this, train and test. And then once they're glued together, you can do anything you want. If you want to standardize it or normalize it, you can do anything you want on this combined data set, and whatever it does to the train rows, it should do the equal thing to the test rows. If you want to add columns or like do a one-hot encoding for categorical things, do it on both of them. So do all your data pre-processing on this train test glued together thing. And then you do steps, do data pre-processing. Okay. And then once you do the data pre-processing, you've added the columns, you've normalized, you've deleted, you've done all the things, then you split it up, split up for training. Okay, so you cut it sort of back into two pieces again. So you have your train and your test, like this. And the advantage of doing it this way is whatever you did in the data pre-processing step automatically gets applied to both the training test and the test set in the same way. And you sort of avoid this kind of bug of if you first do something on the training set and then you try to replicate, trying to do the same exact thing on the test set, sometimes it goes wrong for a reason you don't understand, like things were in a different order or the mean was different or whatever. Whereas if you do it sort of this way with the gluing, then it will go a little bit better for you. So that is my advice, is to try this method to avoid the bug that I told you. Questions or comments about this common bug? Yeah?
For the gluing together, is there anything specific that we need to do?
Yeah, the one thing you might need to do is you might need to add a column in the test set called like sale price and set it to like question marks or something. So when you combine two data frames, there's different ways you can, if they have different columns, there's different ways to mash them together. So you can either make sure to have the setting right to keep all the columns, or you might have to add a question mark to the end. Yeah, and that's also a good thing for you to learn, is like how in the framework we're using in Pandas, how do you actually do that? Yeah, great question. All right, any other questions? Yeah.
If you were to do this, won't your prediction be less accurate for the training set than if you hadn't split it at all?
I mean, it should be identical. Both ways are conceptually exactly the same. And they do the exact, like we're going to do all the exact same steps for both. The only difference is we're trying to avoid this bug of when we do the data like processing on the train set and we do the data processing on the test set, we do them both together to make sure that they actually are identical. When you do it, they should be identical. It's easy to make a mistake and have them not be identical when you think they are. And this way of doing it is the same exact thing, but just like less likely to make a mistake. So I don't think there's any difference between this approach and this approach, except for this approach is more likely to make a mistake. That's the only difference. Yeah. Okay. Yeah. Okay. Any other questions or comments about that? Okay, so in the last 15 minutes here, we're going to start the very basics of classification. So up until this point in the course, we've been talking all about predicting a value, that is called a regression problem. We've been using, the price of a house, or you want to estimate the value on a dice roll, estimating a real number. And from now on, we're going to do some classification. So that's estimating a class. And I have this little warm-up problem for you to see what you guys think about this. Here. Okay. So for regression is in quotes. Unfortunately, the word regression is overloaded. So regression can mean predicting a real number, and it can also mean linear regression. And they both have the word regression, but it means two different things. So regression problems, we're estimating a number y in R, a real number, like the price of a house. Our prediction, y hat of x, so y hat is what we're predicting as a function of the input x. We measure how close we are by y minus y hat squared. This error function, aka loss function, is sometimes called blank. You tell me, what would you call this thing? And then you got to come up with the same thing, but in the classification problem. So in a classification problem, the thing we're trying to estimate is not a number, it is some collection of a set of classes. So it could be like true or false, it could be like red or blue or green, some collection of classes, and the classifier we produce is something y hat of x that is telling you, I think this is red, I think this is green. The true label is y, and the thing we're estimating is y hat. The error function we use for this kind of problem is called blank. What would you use for a classification problem? Okay, those are the two things. Fill in the blanks with a word or a few words to tell me what it is. All right, 10 seconds left. Put in your guesses for these two blanks, these two words that describe how we measure how well we're doing in different things. Okay, I gotta find the mouse. Okay, what happened? The error function is called the residual sum of squares. Yeah, that's right. I think that's technically right. The one I was going for was this one, mean squared error, what's the difference between the sum of squares and the mean square? Then you just divide by the number of points, right? This is the total, and this is the average. Okay, the squared error, very nice. The MSE, amazing, 4 people did that. And the MSE, again, it's some kind of measure of the variance. So variance, very nice answer. As well, mean squared error. Square loss, yen. I think this one is, unless it's dollars, or unless it's currency conversion, is not yen. Okay. All right, very nice. That's what we've been doing up in the course up until now. What is the sort of analogous thing, the equivalent thing for classification? And what did people write? All right, so the misclassification error, very nice, or the accuracy, these are both the right kind of idea. Classification. So this one, classification error, is like true, but for the, the first rule of the tautology club is the first rule of the tautology club kind of situation. Yes, the thing we're talking about is the classification error. Well, what is it? So maybe accuracy is the best one I've seen so far. There's one, 0-1 loss. Yeah, 0-1 loss is also a nice way to say it. Very often people think it's the cross entropy loss, and I'll talk about this one in a second. So it is not the cross entropy loss, it is the accuracy. Let's write it down. Okay. And the timer continues to vex me. Okay. So classification, and we will use accuracy. So our error function so we have y is the true label in the set of classes. Y hat is our estimated label also in the set of classes. So C equals a collection of classes. I think thinking of it as true or false, e.g. true or false, that's a nice example. You're trying to say if something is true or false, or maybe there's three classes. If there's red, green, or blue, you're trying to say what color a thing is. And the error function we're going to use is the are they equal? So if they're equal, what's going to be, you get 0 loss if they are equal, and you get one bad point if they are not equal. They are not equal. So in other words, up until now, if you've been close to the right answer, you sort of pay less of a penalty. If you remember that dice example we did, you want it to be close to the right answer, even if you didn't get it exactly right, which is why the answer was 2.5 and not 2. But for classification, if you get it wrong, it doesn't matter how you got it wrong. You always get hit on the head one time by a big hammer, okay? You get one, that's why it's called a loss function. It's like how much did you lose? You lose 1 point if you get it wrong. And you can write this as, some people write this like this. They say it's the indicator function. So this one is the indicator function of y is not equal to y hat, where the indicator function of some event A means 1 if A happens and 0 if A does not happen. Okay. So some people might call this the 0-1 loss. And if you add this up over all the points, if you average this over all the points, so if you have 1 over the number of points and you do the sum from I equals 1 to n of this indicator function of y is not equal to y hat, this is the percent you got wrong. So percentage of mislabeled points. Okay. And this is 100% minus the so-called accuracy, minus the accuracy, where the accuracy is the percentage of correctly labeled points. So our loss function, the thing we're trying to minimize, is 100% minus the accuracy. The thing we are trying to maximize is the accuracy itself. And I will say, okay, this is a common misconception. There is something called cross-entropy loss. It is, note, cross-entropy loss. Cross-entropy loss is super important and is related to all this, but it is not this at all. So don't mix it up with cross-entropy loss. This is something else. It's something else. And the important thing in cross-entropy loss is in cross-entropy loss, you have not estimated one particular class. You have a probability distribution over classes. And we will do this later, but don't mix these up. Okay, it's something else, and it is something else applies to probabilities, not classes. Probabilities of classes. Okay, and we'll see that later. Okay, and just like we did in our first week of classes about overfitting and underfitting and all that, all of the overfitting and underfitting, all of that applies to classification as well as regression. So that part is exactly the same. And I'm going to show you an example that you might recognize over here. Let's turn on this off. Let's see. Okay, yeah. Here are some points. So there's two classes. There's the 0 class. These are points that have 0. And these up here are points that have 1. So this is a situation where, you remember the cannon, we shot the cannon, and you set the cannon to some angle, and you shoot it. Well, in this situation, we're not measuring how far the cannon went. We're measuring did the cannon work or not. So sometimes the cannon works, and sometimes the cannon does not work. And we're trying to figure out what's working. The blue is the actual probability of the cannon working when you shoot it at a given angle. And so if you shoot it at these angles, it's quite likely to work. If you shoot it at these angles, it's quite unlikely to work. And unfortunately, in real life, you never get to see the blue curve, right? So this is the unknown true probability function. In real life, you only get to see the data of 0s and 1s, and you have to estimate, do you think it will work or not at a given angle? And just like before, the method of having a window, that works just like it did before. So you put some window, and then you count the number of ones versus the number of zeros, and you estimate that as the probability. So you get this kind of estimate where you can change the window size. If you change the window size and you make it really small, you have this estimate that's going up and down and up and down. If you make it really big, then you have a really flat estimate, and you think it's kind of like 50% to work everywhere. And what is your estimate for the class? Is you just say, is it higher or lower than 50%? So if I put in what do I want to do? Higher or lower than 50%? Oh, that's what this purple bar is up here. So everywhere from here to here, I think it's higher than 50%, so I think it's more likely to work. And down here, it's less than 50%, so I think it's less likely to work. So up here, I'm estimating y hat equals 1. Down here, I'm estimating y hat equals 0. Okay, and I can shrink the window. Of course, if I shrink the window very small, I have this really funny estimator that goes up and down. So I think it's going to work. I think it's not going to work. I think it's going to work. I think it's not going to work. And it goes all over the place. But just like before, you want to balance overfitting and underfitting. Right now, we're overfitting quite a bit. And there's some kind of optimal in between like that, where it's kind of doing a balance of both. And that's a lot closer to the real function. The accuracy is like how often the purple, which is my estimate, overlaps with the true, which is the blue. That would be like the accuracy. Okay, so this is everything we did in the first 2 weeks also applies to classification, and it's just we're measuring how we're doing differently. You have to get it exactly right for it to count. This method is essentially the k nearest neighbors algorithm, except for instead of saying find your k nearest neighbors, it's saying find everything within a certain window. In the textbook, they did the k nearest neighbors. I want to do this. Okay, here it is. So this is the exact same kind of algorithm as the sliding window. So in this example, the x's are two-dimensional. There's an x1 and an x2 going up here vertically. And blue dots are one class, orange dots are another class. And for every possible point, we look at the nearby, the k nearest neighbors and have like a majority vote. So on the left side, they're doing k equals 1. So for example, if you're in this little blob over here, your nearest neighbor is blue, so we think that you should be blue. Whereas in k equals 100, it's a lot more of a straight line. So this is a little bit like a very small window or a very large window. And this k nearest neighbor algorithm is a pretty good way to do things if you can balance the overfitting versus the underfitting. So over here, they have a plot of the training error and the test error. And the test error, the thing we actually care about, has this kind of U-shaped curve where the optimal value is somewhere in the middle, right in the middle. What is the k value in the middle? So 1 over k is 0.1, so k is about 10. So looking at the 10 nearest neighbors gives the best test error on the set, and that's what you would want. If you look at the training error, it seems like the training error is getting better and better the smaller you make k, but again, that's just overfitting. So over here, you're plainly overfitting. And so all of that discussion from the first few weeks applies to classification as well as regression, like we did before. Okay, so that was a bit of a review of what we did in the first few weeks, applying it to classification. Oh, yeah, here's the optimal one for k equals 10. And you see when k equals 10, it kind of shifts around a little bit. Like there's these regions where the oranges are encroaching on the blues, and the 10 nearest neighbors to you over here happen to be more oranges than blues. That's why that's part of the orange region and not the blue region. So it's sort of a two-dimensional version of this thing that I showed you over here, which is some kind of funny classification version of the cannonball problem. Okay, any questions or comments about the very, very basics of classification with k nearest neighbors? All right, we're going to do lots more k nearest neighbors starting on Monday's class and onwards. We're going to be classification for a while. Make sure you watch the videos to keep up with it. That is basically all I have to say about the homework, or the project that is due. So the deadline is Friday, not the Friday 2 days from now, but after that. So make sure you start working on that and trying it out. Yeah, I don't know what else to say. If you have questions, please ask them. You can ask them on the forum, or you can come see me after class and we can chat and find a time to meet. Okay, see everybody on Friday. Oh, not on Friday, on Monday.